but I think Leanne will also be recording. So we're very lucky today that Boris Kayser of Fermilab has agreed to Zoom us a colloquium on neutrinos. He's been for decades the leader or one of the leaders in world opinions and the world understanding of neutrinos. Also one of the best lecturers on the subject. So I'll just ask him to start now.
Thank you. Thanks very much for your kind words and for the opportunity to talk neutrinos with everybody. Well, it did work. Now it's declining to work.
And the little arrow key didn't work. Pushing the space bar doesn't work.
No. I apologize. I'm having a technical problem. This was working a few minutes ago, but it isn't now.
Wasn't it something about clicking somewhere?
I just did. Try this. Nope. Try this. Nope.
Well, you can't go back.
Well, you know, I tried to. Yeah, I'm sorry.
We can see your mouse moving around.
But it's
You
not
mean
moving.
this?
What about one of these? Would one of those arrows work?
There we go.
Okay.
All right.
Now, with luck, we will start with a few things that we already know. We know that there are at least 3 ultralight neutrinos. The first one, the second one, and the third one. The splitting in squared mass between neutrinos 1 and 2 is this very tiny number. And the big gap between the third neutrino and the first 2 is some 34 times bigger in squared mass. We don't know whether this closely spaced pair is at the bottom of the spectrum like this, or at the top of the spectrum like that. There is some preference in the data for the normal ordering, but it's really not known yet. There are a number of constraints on the absolute scale of neutrino mass. We know this little delta m squared, and we know this big delta m squared. I just quoted you the values of those parameters. However, we do not know how far above 0 this whole 3 neutrino pattern is. That is, we do not know this gap. We have a certain amount of information about that gap. Cosmology, under certain assumptions, tells us that the sum of the masses of these 3 neutrinos is less than something like 0.2 of an electron volt. And laboratory experiments, notably the Katrine experiment in Germany, tells us that this somewhat strange looking weighted average of squared masses of neutrinos 1, 2, and 3 is less than about 1 electron volt. One way or another, neutrino masses are obviously tiny compared to the masses of anything else that we know about. Now, one way to make leptons is first to make the roughly 100 GeV mass W boson, the carrier of the weak force, which will quickly decay into either quarks or leptons. The leptonic decays are like this. The W can decay into an electron plus neutrinos, or a muon plus neutrinos, or the remaining charged lepton, the tau plus neutrinos. The neutrino that accompanies the charged lepton can be nu1, nu2, or nu3, like this. However, we do know that this nu1 or nu2 or nu3 is a coherent superposition of neutrinos, which is the coherent superposition that couples to the electron and is therefore referred to as the electron neutrino. The electron neutrino is not a neutrino. It is a certain coherent superposition of nu1, nu2, and nu3. There are other coherent superpositions of nu1 and nu2 and nu3. One of them is the coherent superposition that couples to the muon, and for that reason is referred to as the muon neutrino. And finally, there is a third coherent superposition which couples to the tau and hence is known as the tau neutrino. The probability for getting any given neutrino of definite mass, like nu1 or nu2 or nu3, in combination with any given charged lepton, is something that we know. These are not neutrinos of definite mass. Each of them is a coherent superposition of the neutrinos nu1, nu2, and nu3, which are the neutrinos of definite mass. A word about flavor. We speak of the electron, muon, and tau as the three flavors of charged lepton. Correspondingly, we speak of nu-e, nu-mu, and nu-tau as the three flavors of neutrino. But as I have already cautioned, the language can be misleading. E, mu, and tau are particles, each of which has a definite mass. But nu-e, nu-mu, and nu-tau are not particles, each of which has a definite mass. As already stated, each of these three, is a different coherent superposition, a mixture of the particles nu1, nu2, and nu3, which have definite mass, like this. Nu alpha is nu-e, nu-mu, or nu-tau. Nu-I is nu1, nu2, or nu3, one of the neutrinos of definite mass. And there are coefficients in this superposition, which are elements of an object referred to as the leptonic, as the leptonic mixing matrix. All right, now, how have we discovered what it is that we know? The discoveries of neutrino mass and of leptonic mixing have come from various observations of neutrinos changing from one flavor to another, the phenomenon that's referred to as neutrino oscillation. So what is this neutrino oscillation or neutrino flavor change? If neutrinos have masses, as we now know they do, and the leptons mix, as we now know they do, you can have a scenario like this, in which you make, through pion decay and an intermediate virtual W boson, a muon and its accompanying neutrino, which by definition is the muon neutrino, the neutrino that comes together with a muon. If you then send this neutrino on a long journey, like from Fermi lab to somewhere in the Rocky Mountains, or maybe even somewhere in Japan, this neutrino need not remain a new mu. In the course of this long journey, it can change into a mixture of the flavors or into one of those other flavors alone, such as a new E. When a new E interacts in a detector and turns into a charged lepton, the charged lepton into which it turns is an electron. That's what we mean by new E. New E turns into an electron, new mu comes together with a muon. And if you give a neutrino time to change its character by sending it on this long journey, you can have, for example, a neutrino which is born as a muon neutrino like this, interacting instead as an electron neutrino like this, which means it turns into an electron. And something greater than about the last 20 years have brought us compelling evidence that flavor changes like that actually occur. This is not just talking. Now, how does such flavor change occur? Well, as we all know from the days when we were undergraduates in college, in quantum mechanics, particles behave like waves. When a new mu turns into a new E, what's going on is the superposition of nu 1, nu 2, and nu 3 waves that is this incident nu mu changes into a different superposition of nu 1, 2, and 3 waves that instead of being nu mu is a new E. This change from one superposition to another occurs, it can occur, because if nu 1, nu 2, and nu 3 have different masses, which we know experimentally that they do, then their quantum mechanical waves are going to propagate at different speeds at any different energy, because the relationship between energy and speed is mass dependent. So, for example, suppose that the mass eigenstate nu 3 weighs more than nu 1. Suppose we have a neutrino that starts out as a superposition of nu 1 and nu 3 waves, which will be coincident at the spatial location where this starts. But now they propagate, let's say, in this direction. And if nu 3 is heavier than nu 1, at this given energy that they share, nu 3 is going to be moving slower, so it's going to get behind nu 1. The nu 3 wave will be behind the nu 1 wave. As a result, at any one spatial point, the interference between the different waves will be different here. The interference between these waves is going to be different after the waves have propagated than it was here when the waves were born. If you follow through the physics of that picture, the quantum mechanics tells you that the probability P of a neutrino of flavor alpha, like nu mu, turning into a neutrino of a different flavor, beta, like nu E, is given by this formula, in which this is the mixing matrix I introduced a while ago. These are the squared mass splittings between the different neutrino mass eigenstates. L is the distance that the neutrino beam has traveled, and E is the energy of that beam. So what you see is that while initially, when L is 0, the probability for getting a new beta is just delta alpha beta. The neutrino has to have its original flavor. There's been no chance for anything to happen yet. But once it has traveled a distance L, these other terms kick in. And if this mixing matrix is non-trivial, which we know that it is, these terms give you a non-zero probability for this neutrino to have a flavor beta, which is not the original flavor alpha. That's what we mean by neutrino flavor change. Notice that neutrino flavor change requires these forms. These forms are going to be 0 unless the mass squared splittings are non-zero. So if you see flavor change, which tells you that these forms are not 0, that is telling you that these mass squared splittings are non-zero, which tells you that neutrinos have non-zero masses. So neutrino flavor change implies neutrino mass. And that's the big deal about neutrino flavor change. That's the most interesting thing that we have learned from it. It has taught us that the neutrinos, contrary to what was once assumed, are not massless. All right, that was a quick summary of what we know. I would like to turn now to what we don't know. One of the most interesting questions to which we do not know the answer is whether neutrinos are identical to their antiparticles or not. Are neutrinos like electrons, which are not identical to their antiparticles? Or are they like photons, which are identical to their antiparticles? The terminology that's used universally is that if neutrinos are identical to their antiparticles, they are referred to as Majorana particles. If they are distinct from their antiparticles, they are referred to as Dirac particles. All right, now suppose neutrinos are Dirac particles, different from their antiparticles. And let's study neutrinos in pion decay, pi plus and pi minus decay. The pi plus decays typically into a mu plus plus a neutrino. The pi minus correspondingly decays into a negatively charged muon and correspondingly an antineutrino. Now, I'm going to use a capital L to refer to what's called lepton number. An electron, for instance, has lepton number +1. A positron has lepton number -1. That's what we mean by lepton number. This was not a lepton. Lepton number 0. So if lepton number is conserved in this decay, as it's reasonable to assume, since that's an anti-lepton with lepton number -1, this must be a lepton with lepton number +1. So the lepton number adds up to what it was at the beginning, namely 0. Correspondingly, here with the charges reversed, this is going to be an anti-lepton. That means it has lepton number -1. Now suppose that the neutral lepton, this guy, from the pion decay, has a standard model charged lepton creating interaction in some target. The evidence is very good that the standard model interactions conserve lepton. So what we're going to have is a scenario like this. If the neutrinos are Dirac particles, in comes the neutrino, it interacts with the target, out goes some recoil, and the neutrino turns into a charged lepton, not anti-lepton. We will not have the neutrino turning into an anti-lepton. Similarly, the anti-neutrino will turn into an anti-lepton, but not into a lepton. This is if neutrinos are Dirac particles. Things are different if the neutrinos are Majorana particles. All the neutrinos we've been able to study so far, including notably those from pion decay, have been super relativistic. Now, when we create super relativistic neutrinos, the standard model weak interaction, which we think we know very well what it is going to create the thing we call a neutrino, this particle, with essentially 100% left-handed helicity. That is, its spin points like indicated by this arrow against its momentum. In contrast, the thing we call the antineutrino is going to be produced with essentially 100% right-handed helicity. That is, its spin points along the direction in which it is moving rather than against that direction. It is possible that the only difference between these two particles is not that this one has lepton number plus and that one has lepton number minus, but that they have opposite spin polarization. This is an open question, but at the moment, it is possible that the only difference between these two particles is how they're polarized, oppositely namely. If that's the case, there needn't be a bar over here. These are what we would normally call the same object, sorry, except that they are oppositely polarized. Now suppose that neutral lepton from pion decay has a standard model interaction which creates a charged lepton with some target. We observe that when a neutral lepton is ultra-relativistic, if its spin is pointing against its momentum, when it interacts, it's going to turn into an L minus like an electron. But when this object, which has its spin pointing along rather than against, rather than against its momentum, when it turns into a charged lepton, it's going to make an L plus, such as a positron. That's okay. That can happen. What this particle does can perfectly well depend on its polarization, even if there is no lepton number, because as we well know, the standard model weak interactions violate parity. A Nobel Prize was awarded for the demonstration of that. They discriminate, these standard model weak interactions, between left-handed objects and right-handed objects. That being the case, it's perfectly possible for an incoming left-handed neutral lepton, like this one, to make an L minus, while an incoming right-handed neutral lepton, like that one, makes instead an L plus. So the situation we're going to have, if neutrinos are Majorana particles, is that this guy is going to do one thing and that guy is going to do another thing. So this summarizes that. Here is the left-handed neutrino making L minus, but not making L plus, while the right-handed neutrino, which has the same lepton number as here, but is oppositely polarized, makes L plus, but not L minus. We could be forgiven to think there's something going on besides polarization, but really polarization, spin polarization is all that's necessary to explain that this pattern is different from that pattern. And remember the contrast with Dirac particles. Dirac particles, nu makes L minus, but not L plus. Here they're Majorana, nu makes L minus, but not L plus. In other words, Dirac and Majorana behave the same. Here, nu bar, Dirac makes L plus, but not L minus. Here, nu bar, which isn't a bar, it just has opposite polarization, makes L plus, but not L minus. In other words, these Majorana particles behave identically to the Dirac particles. For what we've just shown by this example is that for ultra-relativistic Majorana neutrinos, helicity is a stand-in for lepton number. They may have lepton number or they may not. The helicity can substitute for the lepton number. The behavior of these ultra-relativistic Majorana neutrinos is going to be the same, even though they don't have a lepton number. Majorana neutrinos with no lepton number behave indistinguishably from Dirac neutrinos. Bummer. In order to determine whether the neutrinos are Majorana or Dirac particles, we're going to have to do something a little more subtle. We're going to have to work without neutrinos, yeah. Or we have to find exceptions to this rule. Or we have to work with non-relativistic neutrinos, getting around this problem, because as I'll discuss in a moment, non-relativistic neutrinos can exhibit a big difference, not tiny difference, but a big difference between the behavior of Majorana neutrinos on the one hand and Dirac neutrinos on the other. The traditional approach to see if neutrinos are Majorana or they are not Majorana is to look for neutrinoless double beta decay, the process in which one nucleus, decays to another nucleus through the emission of two betas and no neutrinos. As is well known, the observation of this reaction, which has so far not been obscene, or let's put it, evidence has been reported, but it has not been confirmed. That's a gentle way of saying the situation. This has not been seen. Were it to be seen at any non-zero level, that would imply, first of all, that the lepton number L, which distinguishes between leptons and antileptons, is not conserved. After all, a nucleus is, of course, not a lepton. That's the initial state here. The final state contains two leptons, no antileptons, and a final neutrino, which is not a lepton. So there has been a change in lepton number of 2 units. Observation of neutrinoless double beta decay would therefore imply that lepton number is not conserved. It would also imply, for reasons that are a little subtle, so I'm going to skip the reasons, that neutrinos are their own antiparticles. That is, to my mind, the major attraction of looking, as people are looking experimentally, for neutrinoless double beta decay. Once you see it, you will confirm that neutrinos are Majorana particles. So far, even though experiments have gotten more and more sensitive, it has not been observed. Okay, I have been talking so far about the familiar light neutrinos, but there are a number of theoretical models, such as the seesaw mechanism, which is an explanation, a proposed explanation for why the neutrinos we know about weigh so little. The seesaw mechanism and other models suggest that there also exist in nature heavy neutrinos like GeV mass instead of fraction of electron volt mass. And if a heavy neutrino, which we'll call generically N, weighs a GeV, then it can decay and we can study its decays. There are lots of particles that weigh less than a GeV. It has stuff that it can decay into. And those decays could tell us whether this heavy neutrino, and hence, because neutrino mixing mixes this heavy neutrino with the light neutrinos, if this neutrino is its own antiparticle, all the neutrinos are their own antiparticles. So studying the N decays is a way to tell us whether hence all the neutrinos are or are not their own antiparticles. All right, so let's say a few words about heavy neutrino decays. Among the possible decay modes of a heavy neutrino we're calling N is the decay of that N into one of the light neutrinos we already know about, plus some particle or collection of particles, which of course must be electrically neutral. This particle or collection of particles that I'm calling X could be a pi zero or a pi zero, pi plus, pi minus. There are lots of possibilities. What's been found is that the angular distribution of this system X, the distribution in this angle theta, relative to the direction in which the spin of the parent N points. The angular distribution of the system X from the decay of a polarized N depends on whether N and the familiar light neutrinos are Majorana particles, in other words, self-conjugate, or they are Dirac particles, in other words, not self-conjugate. So this is a way of probing, without looking for neutrinoless double beta decay, whether neutrinos are their own antiparticles. Here is an illustration of the difference. Here is the decay of N into a light neutrino plus some system X as a function of the angle theta between the N polarization direction and the momentum of the system X. It's of the form 1 plus alpha cosine theta, where alpha is some constant between -1 and +1, and gamma is the total decay rate. What's been found is that if the heavy and light neutrinos, N and nu, are their own antiparticles, in other words, Majorana particles, then this parameter alpha is 0. In other words, this cosine theta term is not there. And so the angular distribution is going to be isotropic. I think that's not so hard to believe in, because if neutrinos are Majorana particles, then these two decays are really decays of the same object. So you would expect the decay angular distributions to be the same. In other words, you would expect this second term to be absent. And if it's absent, the decay angular distribution is isotropic. On the other hand, if the heavy and light neutrinos are not self-conjugate, in other words, if they are Dirac particles, then quite generally this asymmetry parameter is not 0. So the angular distribution does have a cosine theta term. It is not isotropic. So the idea is you get yourself a sample of these heavy neutrinos in K on decay, for example, if they're light enough, or in the decay of heavy particles if they weigh more than that. And you see what is the angular distribution when these heavy neutrinos decay into light ones plus X. Here are the values of this parameter alpha for several candidate systems X. X of pi 0, X of rho 0, X of Z0, which requires that the decaying neutrino be quite heavy, X being a Higgs. Here's the alpha parameter. These are, of course, the masses of the corresponding particles, the mass of N, the mass of the rho, the mass of the Z. You see that alpha is quite generally not 0. So this distribution is going to be distinctly non-isotropic if the neutrinos are Dirac particles, but it will be isotropic if they are Majorana particles. So to sum up, the question whether neutrinos, unlike the other elementary particles that we know about, are their own antiparticles is a very interesting question, which we have been thinking about for a very long time, but we don't know the answer. Heavy neutrinos, should they exist, could help us to answer this long-standing question. Thank you very much for your attention.
Well, that was a very nice talk. What struck me especially was the clarity of it. You're a marvelous teacher. Let's see, people must have questions. If you have a question, why don't you just speak up? I think that would be the simplest way to go about this. course, while other people are preparing their question, I'll just say it seemed to me as you were speaking that once you have heavy neutrinos, you have the possibility that they're not ultra relativistic. And,
Yeah. Yes, exactly.
And so that's what's behind this analysis that.
Yeah, when I spoke about analyzing the decay of the heavy neutrino, I had in mind that you're going to do it in the usual way. We try to analyze decays in the rest frame of that neutrino, the heavy neutrino.
Mm-hmm.
Yeah, if you make the heavy neutrino, let's say in kaon decay, and let's say the heavy neutrino weighs, I don't know, 400 MeV. Less than a kaon, but not 15 orders of magnitude less than a kaon, to choose a random number. Then you have the possibility of significant non-relativistic effects, and that's going to help you enormously. Yes, that's right. You need not to be defeated by the fact that the light neutrinos are just zipping along way too fast.
And so experimentally, what's the possibility of doing this, and when might we have some group taking up this idea and giving us an answer?
I'm tempted to punt on that one. Are there groups interested in this? Oh, yes. Both at Fermilab and at KEK in Japan. Yes, people are thinking about trying to look for a heavy neutrino, and if nature is kind and we find one, analyzing its decays. There is interest in this both at Fermilab and in Japan. Even at CERN, there is some interest in this, where you could run the collider on the Z boson, and sometimes the Z boson will decay into final states, which include a heavy neutrino, and the heavy neutrino can in turn decay in one or another of the ways we have been talking about. Yeah, the answer to the question, are people thinking about this, is yes.
Kevin, there's a question in the chat from a student you might.
Okay, so let's see. Does the non-relativistic distinction between Majorana and Dirac neutrinos come from the Lorentz variant nature of helicity? That was the question. I think the best thing is for people with questions just to speak up. That would be simpler.
Okay, I'm waiting.
Well, I read the question. Does the non-relativistic distinction between Majorana and Dirac neutrinos come from the Lorentz variant nature of helicity? I'm a little puzzled by the nature of the question.
Well, let me try saying some things. I think the answer is no. When you no, I could go all the way to the limit where the neutrino is not moving at all. It just has a spin, and that spin points in some direction or other. And if the neutrino is somewhat massive, it can decay, and the decays will probe whether it is a Majorana particle or a Dirac particle, and the helicity is not involved in any central way in that situation. The helicity, well, when it's at rest, it's just a spin. The spin points either up or it points down. That's going to affect the angular distribution of the decay products. But the the Dirac versus Majorana distinction can, for example, be whether one and the same neutrino decays to pi minus with the same rate as to pi plus. That doesn't depend on the spin.
Let's see, we have another, thank you. We have another
Uh,
question from Tusif.
Yeah, thank you, sir. It was a very interesting talk. My question is, whatever the interaction we observed in a standard model, in all those interactions, the lepton number is conserved, but
The lepton number is what?
lepton number is conserved in all the interactions
Yes.
so far that experimentally observed. But if we try to see the neutrinoless double beta decay, so there is a clear indication of lepton number violation. So how much we are sure that we are going to have this lepton number violation decay mode, because it is contradict with established standard model.
If I knew the answer to this question, I would quickly start to write a paper. You're basically asking me what people think without really knowing experimentally. What people think is that at some possibly very small level, lepton number is not conserved. Do we have clear evidence that this has to be the case? No. We have never seen any evidence of lepton number non-conservation, just like we have never seen any evidence of electric charge non-conservation. I think most people believe that electric charge is conserved. You might think it's reasonable to suppose that lepton number is like electric charge. It is conserved too. I think what I said a moment ago is true as a statement about people's beliefs. People suspect the lepton number is not always conserved, but we don't know. Hence, it is very interesting to look for lepton number non-conservation, and that's the point of looking for neutrinoless double beta decay. People have been doing that for many decades, and the limits on the process keep getting tighter and tighter and tighter, and it's never been seen yet.
Okay, thank you, Professor.
Way, is the nuclear physics the problem, or is it just the experimental sensitivity?
Well, I'm not sure what you mean by is nuclear physics the problem. There are some disagreements about what the nuclear matrix element for neutrinoless double beta decay is. And of course, the smaller it is, the lower the decay rate is going to be, even if the process exists. So there is sometimes discussion of whether we fail to see neutrinoless double beta decay, not because it doesn't exist, but because the nuclear matrix element for it is just so tiny that it's below our level of experimental sensitivity. But if you don't see it, you don't see it. And one of the possibilities is you don't see it because it isn't there. I don't know, I shouldn't be laughing. I mean, people have been talking about neutrinoless double beta decay. I remember Henry Primikoff was talking about neutrinoless double beta decay sometime in the late 13th century. Gee, I mean.
Let's see, there's another question there. Nishant has a question.
Yeah, so my question is, if heavy neutrinos exist, what could be the reason that we have not seen one so far?
I'm sorry, is your question if heavy neutrinos exist, how come we haven't seen any?
Yeah,
Well, I have to go now. That was a joke. I do not have to go now. The glib answer is they haven't been seen because it's hard to look for them, but that doesn't tell you anything. Why is it hard to look for them? Well, the heavy neutrino, of course, being a neutrino, does not leave a track. It's an electrically neutral particle. On the other hand, if you have a heavy neutrino, which say weighs 1 GeV, hopefully it will decay before it leaves your detector, whatever your detector is. And it will decay typically into electrically charged particles, which are detected by your detector. So you should see those electrically charged particles emanating from a point in the middle of your detector, and nothing visible has gone into your detector up to that point because you don't see the heavy neutrino itself. People have been looking for such signals. I have seen pictures of possible such signals, but it's not confirmed yet. People are looking. Stay tuned.
thank you.
Sure.
So let's see, do we have any more questions? There are, we certainly have time for more questions. So if you have a question, do speak up. Well, let me ask you a question that's totally irrelevant. There's
Then
been
I'm free to
some-
give an answer that's totally irrelevant.
Right. There's no, this business of the neutron lifetime, the beam and bottle, different, the rates being different in beam and bottle experiments. Do you think there's anything fundamental going on there, or is it just that one set or both sets of experiments have some errors?
My guess would be that it's the latter. I hesitate to say this out loud because, you know, the hit squad may come. No, I think it's not fundamental.
Okay. All right, we have another question. Tim Thomas, I think. Why don't you just
Yeah.
speak up, Tim?
Yeah, can you hear me okay?
Yeah.
Yes, I
I
can.
was struggling to make my microphone work. In the chat box, just as sort of a reference for my question, I put a webpage that I just found, a lovely webpage from Fermilab, neutrinos.fermi.gov. My question is, I'm kind of intrigued by extremely low energy neutrinos. But if you look at the plot at the bottom of this short webpage that I just put in the chat, it looks like the cross sections are just ridiculously low to the point where you can't really do anything experimentally with very low energy neutrinos. Is that correct, or is there something I'm missing? Thank you.
What you said is correct. As the energies of neutrinos become very small, the cross-section for them to interact with your target, whatever your target is, also becomes extremely small. Doing business with neutrinos has never been easy. And when you're in the low neutrino energy regime, it is particularly not easy. You're absolutely correct. You know, Fermilab has been doing neutrino physics now, a lot of it, sending a beam to the Dakotas, sending a beam to the mini boon detector on the Fermilab site. This is not an easy business. And, you know, I feel somewhat guilty. I'm a theorist. I just reap the benefits of the hard work and the rising to challenges of our experimental colleagues. Theory is very easy. I just go to my desk. Yeah, it's hard. You're right. The cross sections are tiny. It's not the only reason it's hard, but that's one of the reasons.
So let's see. Does anyone else have a question? There are some experts in the audience here at the University of New Mexico who haven't spoken up. Would one of them like to?
The oniums?
Excuse me?
The oniums?
No, I was saying that there are some experts in the audience.
Oh, in the audience. Oh, I
Yeah,
see.
yeah,
Yes,
yeah,
yes,
who
sorry, I
are,
meant-
who haven't spoken up, and I wonder whether they have questions or would like to make suggestions. All right, while they're thinking, I'll ask another off-the-wall question. Do you think there's possibly some fundamental limit on the measurement of momentum? And what I'm imagining here is that as the momentum of a particle goes to infinity, is there some inherent error in measuring that momentum? And I'm sort of thinking that you need some huge detector to stop it, but if the detector is huge, you're not sensitive to the recoil of the detector. Does that make sense? Or do you think that in fact, with arbitrarily high momentum, you can still get a precise measurement with enough funding?
Oh, I used to know about funding. Other people may not know what I'm referring to. You do, of course, but so let me explain that. One of the major funding agencies in the United States is the National Science Foundation. I actually worked for the National Science Foundation for nearly 2 decades. Yeah, I was exposed to funding issues. Regarding your question about momentum, unless something happens that involves the quantum mechanical uncertainty principle in a way that we really haven't explored with very large values of momentum, I wouldn't think so, but if something happens there that we have not explored before, that of course would be very interesting. My guess would be no. If the momentum of a particle is very large, in principle at least, you should be able to have an experimental handle on that momentum with a relatively low fractional error.
How would you do that?
Magnetic fields on which we have a very precise control.
Yeah, but if as the momentum of that particle goes to infinity, you need a stronger and stronger magnetic field.
Indeed.
So you say just have NSF funded and.
No, I was hoping the DOE would fund it.
Yeah,
That's the old, let's him fund it.
yeah. Well, let's see. We're getting down to almost an hour. So let's have somebody speak up. One of the experts, one of the neutrino experts may have a question.
The neutrino experts have the answers.
Yeah, well, neutrinos have always been surprising. Well, I'm not hearing anything from some of the local physicists who work on neutrinos. And I think I'm running out of off-the-wall questions that occur to me immediately. So maybe it's just time to thank Dr. Kayser for his excellent lecture, which was really remarkable for its clarity and also for its humor. One of the delightful things about a Kayser lecture is that there's always some humor lurking in the foreground or the background, and that's a charming aspect of his talks. And one would wish others would imitate him, but I guess we'll have to wait for that as well as we'll have to wait for knowing whether neutrinos are Majorana or Dirac.
I'm sorry, they're Majorana. What other kind are there?
Yeah. Well, anyway, thanks very much.
Thank you. Thank you for the opportunity.
Applaud. And is it snowing, by the way, at Fermi Lab?
If it isn't snowing at the precise moment that we're talking, it has been snowing. There's a lot of snow on the ground, and we expect more coming.
Yeah.
Yes,
Yeah.
we have snow. I suspect it is not snowing in New Mexico.
No, we've had very little snow this year. This global warming, it means I don't know, it's been dry and warm. And I really think that this global warming, I mean, we're not going to do a damn thing about it. And it's going to be either geoengineering or we're going to suffer. And of course, I'm speaking of our grandchildren and great-grandchildren, but I don't see the government's doing anything about it. And
Not very much.
yeah.
What is the altitude?
We're a mile high here, roughly a mile high in Albuquerque.
Oh, you're at 5,000 feet.
Yeah, and right at the edge of town, there's a mountain that goes up another 5,000 feet.
Oh, no kidding.
So if we have rain, we get snow on top of the mountain during the winter. And normally we can just go skiing very easily. But I do cross country rather than the crazy kind. But I haven't been skiing once this winter. It's just been too warm. There has been snow on the mountain, but I don't know. It's probably a little there, but you never know. If there's not a lot of snow and you do cross country, you worry, you could hit rocks.
Sure.
Yeah. All right. Well, thanks once again, and good luck.
My pleasure. Thanks for the invitation.
And thanks for just an ideal lecture in clarity and humor. So I guess I'll end it finally, although it's kind of a sad thing to end any Kayser lecture. Okay.
You're very kind. Thank you.
Well, I'm just being honest. Bye-bye.
Bye-bye. Keep well.
Yeah, you too.